Hello, everyone. Welcome to the Informed Data Mining Society webinar series. This is our pleasure to invite Dr. Paul to give a talk, which is actually the first webinar of our Data Mining Society. So I think everyone knows Dr. Paul very, very well. So I probably will just give the floor to the Dr. Paul. So let's welcome Dr. Paul.
Joe, thank you very much for the invitation. I appreciate the invitation to the Data Mining Society. I hope everybody can appreciate my background is for real. That's not a Zoom background. I'm talking here from lovely Florida, which is a new place for me. Let me share my screen here. Let's get going. So I'm going to talk about reinforcement learning and stochastic optimization. These are sort of the buzz phrases, but really I'm talking about sort of universal framework for sequential decision problems. So I started my career, I've worked on a wide range of problems. Every one of these pictures is a snapshot of actual projects I've worked on, starting with trucking, which was my introductory problem, moved into rail, air cargo, manufacturing, logistics, energy and health. I ran an energy lab for 10 years. Even in the lower right, left-hand corner is a robotic scientist. I got into optimal learning for laboratory sciences, which took me into a whole area in a book called Optimal Learning. Basically, I'm working on any problem that involves humans, whether it's engineering or the sciences, personal transportation, finance, supply chains, what have you. So this is anything that involves a human being. Now, whenever you're working in one of these problems, you're going to be trying to do something better. And so you're going to have various goals and objectives: increasing profits, reducing costs, maximize productivity, reduce illness, whatever it is your goal. Now, the challenge is if you want to do something better, it means that you're going to have to make better decisions. And the first step is, what decisions are you making? And oddly, I find often, especially for the more complex problems like supply chains and energy systems and health, people don't always know what the decisions are. You say, well, what decisions are you making? And I can sometimes get blank stares. So once you identify the decisions that you're making, the next question is, how do you make effective decisions? And at some point, somebody's going to raise their hand and says, oh, well, we need artificial intelligence. So let me briefly comment on AI, because there's so many people who throw this term around. In the 1960s and 70s, AI was just rules. If you're eating red meat, then drink red wine, or if a patient has certain characteristics, then use this treatment. In the 1990s, optimization really emerged as a powerful set of tools. CPLEX became really emergent, very powerful. In the early 2000s, AI became machine learning, especially the use of neural networks for pattern recognition. And this became the new AI. And today, many people use the term AI to really mean a machine learning package, and often specifically a neural network. Now, in the around year 2015, a field that has its roots back in the 1990s called reinforcement learning started to emerge. And this is the first time there was really new attention given to making decisions. So the 2020s, what's new? I'm going to say it's sequential decision analytics, which is sort of the next stage past what people classically call reinforcement learning. So I'm going to go through a series of steps. I'm going to start with what I call the 5 layers of intelligence. Now, in the 5 layers of intelligence, the one that I'm most interested in is that top layer, decisions. But we really do have to start with the first 3 layers, because in any company, information acquisition, where is the truck, how much inventory to have, what is the state of human body, what is the state of the world, is that foundation, and that remains a very hot topic. Communication and storage. Once you collect that information, you have to communicate it in storage. And then you get to transactions and execution. And this is where you'll often find these rooms full of people sitting at computers, making decisions and running some operation. So let me jump up to the 4th layer, learning. So this is where a lot of people say, oh, this is artificial learning, or so they'll even talk about the AI. Machine learning comes in 4 broad categories. Pattern matching is this picture of a flower. Classification, what product should I offer this customer on the internet? Inference, how will an increase in price affect market demand, or what is the condition of a piece of equipment? Probably a lot of the data mining society lives here. And then good old-fashioned prediction. Here's history. What do I think is going to happen in the future? Now, whenever you're doing machine learning, you're basically taking some mathematical function, and these fall in one of three overlapping classes: lookup tables, parametric models, non-parametric models. And somebody's going to say, well, wait a minute, where's neural networks? Well, they're sort of tucked in between parametric and non-parametric. Small neural networks are absolutely parametric models. The deep neural networks technically are classified as non-parametrics. Whatever it is, this is our library of tools that we can use to fit. So let's say that I have a fitting problem. Let me pose it as an optimization problem where I have to come up with some function. Let's imagine that I want to predict demand as a function of price, and somebody comes in, and this happened to me in an e-commerce project, says, oh, let's just do a linear fit. And I'll say, okay, let's take the data set and find the best linear fit. Now, somebody else could come bounding in and say, well, no, it can't be a line. It has to be some type of an S-curve. And I'll say, fine, let's find the best S-curve. And today, somebody's going to say, well, we should fit it with a neural network. And my only word of caution here is neural networks have a lot of parameters, and they tend to be vulnerable to overfitting. But whatever it is, you're going to be choosing from among these different classes of functions. So you're going to want to pick the function class. Usually that's done by a human. This is where somebody knowledgeable in data sciences, machine learning will say, I think this class of function would work best. And then the machine will kick in and say, here, I will do the search over the tunable parameters theta. Now you need the big data set, because I'm going to need a data set to fit this function. So machine learning, they will call this supervised learning. Brief word of caution with neural networks. Let's say I have a news vendor problem where I have an order quantity and then I observe some random profits. All those blue dots are random observations. If I take all those random observations and fit the neural network, I get that squiggly function where I know that the true function is that solid red line. I know it's smooth and concave. The neural network doesn't know that. And with the noise, you tend to get this overfitting. Here's another example. Demand is a function of price. As you raise the price, the demand goes down. Now, if I take actual observations, I get the red dots. And if I try to fit that with a deep neural network, I get the green function, which is obviously a complete mess. Although, you can see it sort of trends downward, but it behaves in a crazy way. This is one of the limitations I need to often communicate to people. Neural networks are a powerful tool, especially for deterministic problems, pattern matching, but they struggle when you have structure such as monotonicity and noise. So anyway, let's get to my favorite topic, decisions. Now, decisions, you have all these people sitting computer making decisions. Today, a few decades ago, 1990s, this looked very high tech. Today, this sort of looks like a Model T assembly line in 1908. And this was a great breakthrough in 1908. But the simple fact is, fine, we've sort of been there and done that. We know about that. Today, what we're much more excited about is something like this, where we want robots building the car. We want to have robots making decisions. We want to get rid of that room full of computers. So let's take a brief return visit to all of my favorite problems. Behind every one of these problems are decisions. And every one of these boxes is a question that requires an answer. There's a choice. And clearly, if there's a choice, certain choices are better than other choices. So we want to pick the best choice, which means we'd like to optimize our decisions. Now, decisions come in three broad categories. I have decisions that act on physical resources, managing inventory, moving drivers, scheduling nurses. We have financial decisions such as pricing, insurance, managing investment or hedging contracts. And finally, we have informational decisions, sending and receiving information, marketing and advertising, running experiments in the lab, testing drugs. This is all decisions about collecting information. Now, there's different time frames. So, for example, strategic planning in a supply chain, where do I source parts? How much production capacity to have? What markets to serve? Tactical planning, I may want to make a decision now, such as ordering product from China that's going to arrive a month or 2 or 7 into the future. Pricing decisions, personal scheduling, these are making decisions now that have an impact on into the future, and then I have the real-time decisions that execute now. So I like to think of strategic planning design as decisions that you're simulating in the future that don't depend on the state of the system now. Tactical planning I use to refer to decisions that I have to simulate in the future that do depend on the state of the system now. And then you have the real-time execution decisions where you act on the state of the system now. Now, these could be made at any levels in the organization. And my only point here is I'm not restricting my scope of decisions. As far as I'm concerned, any type of decision made over any time frame, made anywhere in the organization, is fair game for sequential decision problems. Now, we're all familiar with deterministic optimization. We have low-dimensional decisions like what's the best path if I'm at node 2, where do I go to next? Or maybe I need to optimize all my facilities around the world. That's a very high-dimensional decision that I have to optimize. And the math programming community has really mastered these problem classes. I've gotten to the point where I don't even think about these problems. Even if they're integer, I just say, oh, it's integer, so what? Make it an integer variable and solve it. There's this wonderful language of math programming. Everybody in OR is familiar with this. I often talk to managers who are not, but we all know that this notation is taught around the world. There's thousands of people from any country that learn this language, and they learn how to go to a physical problem like an airline, put the physical problem into this mathematical language, put it into a package, and out comes an airline schedule. So this is a standard language that we're all very accustomed. Anybody who writes a paper, and we all bow down to George Danzig, who established that language. And it's beautiful because we all know in this world of all the different languages, it's very nice when we all have a common language to speak. Now, let's come back to my set of problems. So we've got all these problems, starting to get used to this now. Behind each of these is a decision. Now, every time I make a decision, information comes in that I didn't know when I made the decision. So here is a bunch of boxes that correspond to each of the decision box. And this is something I would learn after making any of those decisions, which means whenever I made those decisions, it had to be made under the uncertainty of this information that had not yet arrived. So these are all sequential decision problems, and I'm going to claim most problems are sequential decision problems. Decision, information, and information that arises after a decision is made is not known when we made the decision. So for example, inventory management. I make a decision to order inventory, which could arrive right away from an Amazon warehouse, or it might arrive weeks or months in the future. Then I observe the demands for that product. Then I make more inventory ordering decisions. I see more demands, so on and so forth. So these are fully sequential decision problems. I now work at a company, Optimal Dynamics. It's based on software I developed at Princeton, dispatching, assigning drivers to loads. And as you make the decision to assign drivers to loads, new information about new loads is coming in, or weather delays or equipment problems. Maybe you're in health and you're testing vaccines. You have to make a decision of what vaccine to test, what dosage, which people. Then you get the information about how people respond, which people want the vaccine, whether it actually reduces the incidence of disease. And coming from a Department of Operations Research and Financial Engineering, I have to mention financial trading. We had the buy-sell decisions. Prices are going up or down, fully sequential decision problems. Now, here's a very simple sequential decision problem where I take what I know now, and let's just assume that I can buy, sell, or hold an asset. That's pretty simple. And after that, the price might go up, down, or stay the same, and then so on and so forth. And in almost no time at all, this toy little problem explodes. And it's a toy. I mean, this doesn't come close to the big resource allocation problems that we run into in everyday life. So let's talk about modeling sequential decision problems. Now, anytime you want to take any physical problem and get it on the computer, you've got to go through the process of a mathematical model. Now, in deterministic models, everybody speaks that same language of George Danzig. And so this is a very powerful construct. By the way, the same with machine learning. People sit down with machine learning. There's a fairly standard notation. No matter where you've been trained, you're roughly writing the same mathematics out, and people know how to talk to each other mathematically. This is not true with sequential decision problems. When you get into the world of sequential decision problems, you enter what I like to call the jungle of stochastic optimization. And behind every one of these terms is a book sometimes a whole series of books. There's a whole field called optimal control. Every one of these terms is a different field. You could get a PhD in any one of these books and spend years of your life, sometimes an entire lifetime, just working within the domain of each one of these books. There's about 8 fundamentally different mathematical notational systems. And then there's some derivatives where people borrowed from each other with adaptations, like the way reinforcement learning borrowed from Markov decision processes. And so this is the jungle. It makes it very hard to write papers about sequential decision problems. And a lot of times what you have with these books, by the way, this includes my book on ADP in the upper right-hand corner, not only is a particular modeling style, but each book is really emphasizing a tool for solving the problem. So let me talk about how to model a sequential decision problem, because it sounds complicated, but it really isn't. You have a state that is what you know or believe. Then you make a decision. This is some action that acts on the state variable. And then new information comes in, and this is the information that I didn't know when I made the decision. So we've already seen this. Now, each time we make a decision, we receive a contribution or incur a cost. Obviously, it depends on the decision, but it may also depend on dynamic information, the state variable. Now, we're going to make decisions with a method. I'm going to use the word policy. There's many terms that could use this, but I think the most common in the literature is the word policy. But this is something to be designed later. And this is a major point of departure with all those books, because I'm going to sit here and model, and I'm going to say, don't worry about how to make decisions. We will get to that later. This is a significant point of departure from those other books. Now, the state variables evolve using something called a transition function. Give me the state, give me what decision you make, tell me the new information arrive, and I can tell you the new state variable. And our goal is to find the policy that maximizes some objectives, such as the sum of expected contributions. And I want to find the best policy, but we will get to that later. So I like to summarize all sequential decision problems using 5 core components. The state variables. State variables come in 3 flavors. One is the physical state, like an inventory. Then you can have other information like prices and weather. And you can have beliefs about quantities and parameters that I don't know perfectly. So these are all statistics relating to probability distributions. For decision variables, I come from OR, I like X, but there's whole communities that use action A, and the controls people like control U. Now, I'm going to specify at this point the constraints and then introduce the notation for a policy to be designed later. The exogenous information variables, WT plus 1. This is that new information that comes in after I make a decision. Then we have the transition function that tells us how the state variable evolves over time, and we have an objective function that tells us how well the policy is performing. These are the 5 elements that describe any sequential decision problem. So all of those problems in the picture on the right can be described with these 5 elements. It's like math programming. We always write down objective and constraints, and we can describe any deterministic optimization problem that way. And it's been fabulously successful. I can describe any sequential decision problem using these 5 elements. And yet the world doesn't agree on this yet. So now I sometimes find it nice. I'm so used to the classical OR way where we do the objective function first. So we might specify the objective function. Here I'm going to emphasize there's different styles of objective functions when you deal with sequential decision problems. I might want to maximize the expected sum of rewards, or I may want to do a bunch of experiments and only evaluate how well I do at the end, which I call the final reward. And maybe we don't want an expectation. Maybe we want a risk metric of some form. So then you have the transition function. Now, by the way, buried in the policy are the constraints at time t or iteration n. The transition function describes how we evolve over time, but then you also finally have that dimension of the new information. I need the initial state, which can have beliefs, and then the evolving exogenous information. Here it is, one slide. I can use this to model any of the books in that picture. I can take all of those books, take any problem in there and write it down with this mathematical framework. And at the end of the day, I'm always optimizing over policies. Okay, so remember, in deterministic optimization, you min and max over X. In sequential decision problems, we min or max over policies. Now, I like to think of 6 steps in modeling sequential decision problem. Starting with the very beginning, step 1, I cannot create a mathematical model unless I have answers to the following three questions. What are my performance metrics? What types of decisions am I making? What are the sources of uncertainty? This is plain English, no math. In fact, I have found there's a lot of nice complex problems where even if you're never going to do a mathematical model, give me the answers to those three questions. I endlessly find myself with people saying, oh my God, the COVID problem is mind-bogglingly complex, it was a headline from USA Today. And I'm like, it's not really that complex. You just have to break it down. Once you have the answers to those, now start writing out your 5-step mathematical model. I now have 2 steps. The first one is modeling the uncertainty. So that's actually part of the modeling process, but I need to get my uncertainty modeling. And a lot of these sequential decision problems, this is actually the hardest part. Step 4, designing policies. I'm going to get back to that. 5, put it on the computer, and maybe I'm either optimizing a real-time system or simulating something from which I'm doing strategic policy analyses. Step 6 is the implementation, either in the field or the results of whatever strategic plans. So let's take to the next step, modeling uncertainty. This is a huge step. It's so huge, I'm only going to give you one slide, just because I don't want to pretend to cover this. Chapter 10 of my new book, I identify 12 classes of uncertainty from the perspective of models. So this has nothing to do with any application area. These are just ways in which uncertainty can enter the modeling. Think of this as a list of 12, and then you go to your actual application, such as a supply chain problem, and you say, okay, do I have observational uncertainty? Well, guess what? There's a lot of places where I don't know the inventory. Prognostic uncertainty, yes, the forecasts are not perfect, and you can go down the list. You may not have all 12, but it's nice to check off each one. This is a huge area. Anybody can easily have a career just on this problem. It's fantastically rich and important, and this is all I'm going to say about it in my talk. So let's get to this problem of designing policies. So I get a lot of people asking, what do you mean by a policy? So a policy is a method that makes a decision using the information in the state variable, ... any method. Biggest point of confusion is people will say, oh, by policy, you mean like an inventory policy, order up to. And I'm like, well, yeah, but that's not the only way to make decisions. I'm up to about 45 different ways of, in English to words that effectively mean policy. So you pick whatever you like. I have a spreadsheet, tinyurl.com, policies and decisions. At one point I was down in Brazil and somebody translated everything to Portuguese. If anybody has a native language other than English or Portuguese, please feel free to go to that spreadsheet and do your own translation. I'm going to go with the word policy. I have people who'll say, well, wait a minute, that's problematic for me, but okay. Policy is any method for making a decision. So my modeling framework, I introduced notation for policy. Now we're going to say, all right, let's go design that policy. Now, understand, I use this phrase, model first, then solve. By the way, model first, then solve is what we always do in deterministic optimization. We always write a model and then go design an algorithm. This is absolutely standard. And yet you go into those books on the right, and every one of them has come to this problem with a hammer in their hand. They've already got their pet method, Bellman's equation, or look-ahead policy, or model predicted. These are all methods. So I like the method of deterministic optimization. Model the problem, then go design the policy. Now, one thing that we're going to have to do is to evaluate a policy. There's 3 broad strategies. The journals are full of theoretical proofs, optimality proofs, regret bounds, asymptotic convergence. And my students have written a bunch of these papers. They're a lot of fun. However, once you start getting to realistic problems, you're going to probably end up doing some numerical simulations and, maybe using a big cloud computer, but laptops are pretty powerful. And there's a bunch of problems where you probably just cannot write a simulation, and you're going to have to evaluate it in the field. And so sometimes we have learning by doing, whatever method that you like to use. So now let me compare sequential decisions to machine learning. And I want to bring out that there are really close parallels. It's almost easier for me to compare sequential decision problems to machine learning problems than it is to compare to deterministic optimization. So both of these are optimization problems. In machine learning, I'm trying to come up with a function. We call it a statistical model. In sequential decision problems, I'm trying to come up with a function. We call it a policy. In machine learning, I need a training data set to fit my function. In sequential decisions, I do not need a training data set. I need a model. Okay. Other than that, I'm roughly doing the same thing on both sides. I'm searching over functions and searching over tunable parameters. So let's talk about how do we search over policies. So there are two fundamental strategies for designing policies. The one is I call the policy search strategy, where we search over classes and methods to find the methods that work well, that work the best over time. I can divide that into two subclasses. And then we have look-ahead approximations where I design policies by optimizing into the future. And once again, these divide into two subclasses. Let me start with the first of these. So the first of the two subclasses I call policy function approximations. So inventory policies, order up to. Inventory goes below some theta min, order up to theta max. When the price goes below a lower price, or sell when it goes above a higher price. In other words, these are policies that are parametric functions, and I have to tune the parameters. But basically, a PFA can be any lookup table, linear, nonlinear model. It can be a neural network, non-parametric, any of the functions that you might use in machine learning. So the second class, cost function approximations. Now, this is a term that I've introduced. You won't find it in the academic literature. It's widely used in practice. And so you learn about a CFA and you're like, oh, yeah, well, everybody does that. I'm trying to find the shortest path to a destination. Now, so we think of one decision as the path, but another decision is when do I leave? How much time do I allow? And I may say, okay, Google Maps is fine at the path, but when it says 40 minutes, I'm like, I don't know. I want to be safe. I'm going to allow an extra 15 minutes. That's a tunable parameter. So I have an optimization problem, the shortest path, and a tunable parameter. Maybe I'm scheduling nurses, but instead of scheduling them for a 40-hour work week, I schedule them for 32 hours because they're nurses and random stuff happens and I need some buffers. The last one is an actual optimization problem widely used by the tech companies. Let's say X is a product or an ad that I want to advertise, and I want to pick the product or ad that gets the most ad clicks. So let's say I have an estimated revenue, but it's just a rough estimate, and maybe I had some bad luck, and maybe X is a great product, but I just end up with a low estimate. So what I'm going to do is take the standard deviation of that estimate, multiply it times theta, add the two together, and then choose the product or ad X that has the maximum value of the two of those. So I have an optimization problem, the argmax, and I have a tunable parameter theta. This is widely used. I'm going to get back to that in a few slides. Oh, no, I'm not. I'm going to get back to it right here. So here's an example where I'm trying to find the best catalyst to create a material with the highest strength. So I had 70 of these catalysts. And by the way, as happens in the real world, these are not all independent. If I learn something about one, I've learned something about others. Let's say each of the 7, I have a performance, but I have an uncertainty. I have a belief about it. And so the 5th and 6th ones look pretty good. The second one doesn't look that good, but I'm pretty uncertain and it may be really good. So which one do I try? Now, I may try that 7th one and I get a pretty good observation, which updates my belief. However, updating the belief on the 7th one may allow me to update all the other beliefs because there's elements in common that if this works well, others might work well. Maybe they have an inverse correlation. So here are various simple policies widely used and studied in the academic literature. They each have an argmax. I'm always trying to find the best catalyst in this case. I always have a point estimate. There's my point estimate. I always have some uncertainty metric. And then I have a tunable parameter. So of these, I happen to have gotten a lot of success with this middle one called interval estimation, where I take the point estimate and go up some number of standard deviations. So let's say that tunable parameter is 0. That means I'm just taking the point estimate, and that means I would take that 5th one. But what if I set the tunable parameter 2? Now I'd like that 7th one because the upper tail is better than anything else. So the question is, how do I set this tunable parameter? Well, that's an optimization problem. I have a policy, and I'm going to run some number of experiments and end with what appears to be best at the end, which is a function of theta. Now, what I'm going to do here is I'm going to test this policy by tuning theta, and I'm going to compare against a policy I'm very proud of, the knowledge gradient policy. This is something we invented in my lab, and we especially have powerful tools for this setting of correlated beliefs. And boy, were we proud of this up until we found that it was losing. And this was very surprising. And I went to the student and said, wait a minute, Ilya, it's losing. The thing is, if you take a very simple policy that's fundamentally well constructed and tune it well enough, you can outperform much more sophisticated policies. However, you do have to tune it. The knowledge gradient doesn't have any tunable parameters. And that IE works best if you've tuned it well, and otherwise it can work quite a bit worse. Now, this whole idea of optimizing with tunable parameters, all you have to do is look around. Airlines do this all the time. They put in schedule slack. Manufacturers have buffer stocks. Grid operators for electric power generation will plan for tomorrow, and they always put in extra generation in case of an outage. And then we talked about that time with Google Maps where we add in some buffers. I even have a whole web page on this, tinyurl.com/CFA policy. Now, by the way, I have a few URLs in this talk. You don't have to write any of them down. At the very end of the talk, I'm going to have one URL that covers everything. However, this web page I put together when I realized that this whole concept of cost function approximations was new. I created a whole web page for it. If I were starting my career over, I would be working on this. Now, both PFAs and CFAs have tunable parameters, and you have to tune it. So here's a case where I have two tunable parameters. The thing is, you then have to run simulations, and the simulations are noisy. So I can tune it in a simulator. That's where I'd like to be able to do it. Some places you have to tune in the field, and boy, is that an area that needs some more research. The one thing I will tell you is that when you're doing tuning, in a simulator, you might do derivative-based, or in a simulator or the field, you might do derivative-free. Both derivative-based stochastic search and derivative-free stochastic search, both of these are sequential decision problems. For stochastic gradients, that step size alpha is the decision. In derivative-free, I have to guess at the next point on the function. So you have to solve a sequential decision problem to get the right values of theta to solve your original sequential decision problem. Hope everybody's having fun. So let's go to the second class, look-ahead approximations. So now I'm going to try to make good decisions by looking into the future. So let's take Dorothy and the Wizard of Oz trying to get to Oz, and she has to pick the best next step. The way we're going to do that, so this looks very trivial, but wait until you get to this function. This is where we have the immediate cost or contribution of a decision, and then we have all that downstream stuff. And so this is going to be for problems where I really do need to think about in the future. And boy, is that a complete mess. Problem is, we're going to have to roll up our sleeves because we're going to need to use this. So let me first walk you through this using a familiar picture of a decision tree. I start at a state. This is what I know. I have a set of decisions. I want to make the best decision. But after you make a decision, something random is going to happen. And then I have all that future stuff. Now, all of those square nodes are places where I have to make decisions in the future. So each one of these are decision points, and I'm going to need a policy that indicates what decision I would make if I land in that box. And then I have all that crazy random stuff in the future. Needless to say, this is hopelessly uncomputable, but I can't just throw it out because of that. So one strategy is with look-ahead approximations. I can take a piece of it. So let's take that function that depends on the state at st plus 1 and say, well, that's a function. Let's call it a value function at time t plus 1. This is the basis of Markov decision processes. And under very special cases, you can compute that exactly, and at which point I have an optimal policy. Now, generally, you can't. So I can approximate. So now I bring in the tools of machine learning and approximate dynamic programming and whatnot, and do some sort of machine learning method. But I still have that expectation. That tends to be problematic. It's really a problem if X is a vector. Now, one way to get rid of that is use something called the post-decision state variable. I ran into this many years ago. It was a huge breakthrough. Notice that my argmax is now a deterministic optimization problem. Now I'm opening the door to solve very high dimensional X's. Now, if you're a computer scientist, you're going to throw all this stuff together into something called a Q factor. And this is the basis of reinforcement learning, although I think they're starting to learn that value functions are fine. Anyway, Here's an actual example of approximate dynamic programming that I developed in my career. It's the basis of this company, Optimal Dynamics. I'm assigning drivers to loads. I could have hundreds or thousands of drivers, but I have to think about what might happen in the future. So I want to sit and think about, what do I do now? But instead of optimizing over that very complex, high-dimensional and stochastic future, I'm going to approximate it using the downstream value of a driver. Now, this is the value of a driver. It's an approximation. It's around the post-decision state, so I've gotten rid of my expectations. This is a problem I can easily solve for 10,000 drivers. This thing scales. So this has been very powerful. Here, the blue rectangle is all the drivers and loads at time t. Here's the value of drivers and loads in the future. We can now simulate in the future, and we do this iteratively. And over the iterations is when I'm learning the values. Here's actual data from 11 different trucking companies from Optimal Dynamics, where at the initial time period, all the downstream values are 0, and we can see the performance of the company steadily improving as much as 20 to 40%. Here's an actual animation. I'm showing individual drivers, all their rules, picking loads, thinking about the future, optimizing, sending drivers to good region, getting them home on time. This is very real world. This is a simulation we did for Schneider National. Now, value functions, it turns out, and I spent 20 years, I have a 500-page book, and I'm here to say VFAs are a very powerful strategy for a very small set of problems. It is easily that if you go out and work on a real-world problem, it is easily the method that you are least likely to use. Often, you just can't do that value function to any approximation, and so what you do is a look-ahead policy. The way I do a look-ahead policy, I use the same notation, state, decision, information, but I put tildes on everything, and then I start approximating. Now, all of these variables have 2 time indices. The first time index t means I'm making the decision at time t, and then you have a t prime in the future because I'm peeking forward, but I'm peeking forward given what I know at time t. Now, I have all kinds of ways to approximate. I can approximate the exogenous information. I can use simplified policies. I can look at just a few time periods in the future. I can streamline the state variable. There's different tricks. I can use simplified policies. So there's a lot I can do, and there's a lot of art here. But let's say I do myself a look-ahead policy that I can solve, and I look ahead and I solve it and I get a decision now, I implement it, look ahead, solve it, get a decision now, look ahead, solve it, get a decision now. This is something we use so often, we often don't even realize we're doing it, such as with Google Maps. Here I am in Hartford, Connecticut, upper right-hand corner. It's 4 o'clock in the afternoon. I'd like to get back to my home in Princeton in the lower left-hand corner. And there's Google Maps running me right through New York City. And I'm like, whoa, Google Maps. Now, this deterministic look-ahead is often referred to as model predictive control. There's a whole book on it. There's a whole field called MPC. It usually means a deterministic look-ahead. And I'm saying, wow, given what you know now, maybe New York's okay, but that's really high risk. What I'd rather do is to say it could be really bad. Here's another path that's a little bit longer down below, about 5 minutes longer and much safer because I go around New York City. Now, that is actually using the concepts of this field called robust optimization, an entire book on that topic. And then you have stochastic programming, and even ADP could be used. So these are entire books on how to approximate stochastic look-aheads. And that's fine. It's a very rich area. I have an entire chapter of my new book dedicated to all types of look-ahead policies, including deterministic look-ahead. So let's take a deep breath. I've just gone through all 4 classes of policies. I've gone through the 2 policy search policies, the PFAs and the CFAs. I've gone through the 2 look-ahead classes, the VFAs and the DLAs. By the way, I like to further divide the DLAs between deterministic look-ahead because they're so popular and stochastic look-ahead. And sometimes deterministic look-ahead, like Google Maps, really does work out quite well. Sometimes I really just need a stochastic look-ahead. These are the whole 4. Now I'm going to make a really strong claim. I'm going to claim these 4 are universal, but they cover every method for making decisions described in the research literature or used in practice, including methods that haven't even been invented yet. My new book does cover classes of methods that I think haven't been invented yet, although I can't be positive. This means that if you go out in the field at a company, they're already using one of these 4 classes. So you can have your favorite method because you proved a lot of theorems with this, and you go into, I don't know, a hospital or an energy company, and you're going to find that there's reasons why they're not using your pet method. And there's a bunch of reasons. In chapter 11 of my new book, I have a whole discussion of some of the soft issues. But it does mean that it's a good starting point because I can go into any situation and say, okay, I'm going to model what you're already doing. And I think that's quite powerful. By the way, this is a more general version of machine learning because the lookup table, parametric and non-parametric, is also universal. That's all the analytic functions. Now, here's a little problem, a little energy storage problem that we made up. I can get energy from a wind farm or the power grid. Power grid, I assume, is an infinite source, but at very random prices. I'm serving a fairly predictable load, and I've got my Tesla Megapack in there to absorb all the variations. Now, this is real world data. I have data. This is 24 hours of wind. The black is the actual energy from the wind farms. And all the other lines, that line I just highlighted is a 24-hour forecast starting at midnight. And all the other lines are the updated forecasts as we step forward in time. And you can see they change quite a bit. Wind is really hard to forecast. So you have these rolling forecasts, huge errors. And everything's time dependent. The load is very time dependent. How am I going to solve this problem? Guess what? I really want to use a deterministic look ahead. And buried in my deterministic look ahead is that wind forecast. There's the wind forecast. And I just illustrated how bad this is. So what am I going to do? So if I'm a PhD student looking for a fancy algorithmic paper, I'm going to say, oh, I'm not going to do this. I'm going to do some sort of fancy stochastic model. But let's say I'm trying to do something practical. What I might do is say, okay, I know that forecast isn't very good. How about if I just throw in a discount factor? So my theta t prime minus t depends on how many hours in the future. So if it's 1 hour out, 10 hours out, 24 hours out, and now I have what we call a parameterized policy, but it's still a deterministic look ahead. So it's very easy to solve. The only problem is tuning those thetas. So like Google Maps, I can optimize in the future. Very simple, super fast LP. It only tells me what to do now. Then I roll forward, update my rolling forecast, solve it again, very quick, update my rolling forecast, solve it again. This is just like Google Maps, very practical, but you got to tune those thetas. So we set up a problem where we said, let's start off by assuming that my forecast is perfect. Okay, so I have the perfect forecast of wind. You would expect that those thetas would all come out equal to 1. Guess what? They do. So if you have a perfect forecast, you want all those thetas equal to 1. That was a big sigh of relief. People know that things don't always work out this way. But once I put in the stochastic forecast, now they move all over the place. And those upper lines where the optimal theta is a good bit smaller, closer to 0.3 or 0.4, these are the forecasts for first hour, second hour, third hour, fourth hour out. And if you start off and say a baseline with theta equal to 1, so let's make that our base, which isn't terrible. It's sort of the standard thing. But after I've optimized the thetas, I get about a 30% improvement, and that's kind of nice. That's not a small improvement. And in the field, it's no harder to solve. Now, in the lab, I've got some work to do, but that's where the work should be. Have somebody figure out these crazy thetas. You go to the field and you have something simple to implement. Don't try to get this published, though. Here we created 5 problems. This was done by a postdoc at the time, Stefan Meisel, who's now at University of Munster. Stefan put a huge amount of work into this. He created 5 different problems. We made up the problems. We played with, how accurate were the forecasts and how time dependent or stationary it was. And so we had 5 different problems, and we were tuning it so that we could bring out the strengths of each of the 4 classes of policies and the hybrid, And so we made each of these 5 problems, for each of these 5 problems, one of the 5 policies worked best. And this is my story here is this means you can't go running around and saying, oh, like I know a colleague who says, oh, model predicted control, which is what he means is a DLA. So here you see the DLA could give me 74% of the posterior optimal, but it could give me almost 100%. So the thing is, you really do have to be open to all of them. And there are some problems where the DLA is utterly unsolvable. So let's go back to my bridge between machine learning and sequential decision. So we know that we've got all these different problems for machine learning, and one reason why people like the deep neural networks is because it'll fit anything. Of course, that's a problem as well as a feature. Over on my sequential decisions, we have the policy function approximations. All the methods for machine learning fall in PFAs. Okay, so if all I do is focus on the PFA class, I'm doing almost exactly what we're doing in machine learning. I just don't have a training data set. I have to have an actual model of the problem. The thing is, I still have the other three classes of policies, each of which are themselves optimization problems. And boy, is there a lot of confusion. The number of people who will say, take a stochastic look ahead, and they don't realize it's a policy to solve a problem. They think it is the problem. And if you get an optimal solution, that it's somehow optimal. It's not optimal. It's not an optimal policy. So you've got to write out that simulation, the basic model, then go design your policy. And you're not going to try out all four classes. There are some problems where it's just screaming one or two classes are probably just going to be better suited than others. Now, I often get people asking me, how do I choose among these? There tends to be a trade-off between how hard the policy is to compute and how hard it is to create. So PFAs are easy for simple problems, but they're very complicated for hard problems. So they're hard to create, easy to compute. Stochastic DLAs are not really that hard to create, but then they're hard to compute because I have to look into the future and then simulate many scenarios. And then, of course, there's a whole frontier of these. So one thing that I would like to point out, if we go back to my library here, there's a very substantial academic bias toward Bellman's equation. All 10 of these books either exclusively or predominantly build on Bellman's equation. Academics love Bellman's. Whenever we teach our students, we're teaching Bellman's equation. I'm here to tell you that is the least useful of the four classes of policies. Now, if we're not doing Bellman, we're probably doing stochastic look-aheads. Okay, fine. Stochastic look-aheads are useful. Again, not the most useful. I'm going to claim, so when we have our search order functions, you see how we have, I could have a linear fit for the demand as a function of price or a nonlinear, and then use our big data set to do the parameter tuning. In parameterized policies, often the most popular policies, the one that we're most likely to use, are the PFAs and the DLAs, CFAs, and the parameterized DLAs. I mean, these are the big three. This is what most people do. And if you ever go into anybody who says, oh my God, here's this academic, he's coming in with something complicated. If you spend some time with whoever's already making decisions, you're going to find they're already using one of these three classes, and which one tends to be pretty obvious from the problem, buy low, sell high, type of things. But you still have the parameter tuning. Okay, so both of these still have parameter tuning. So I'm going to close out with my favorite pitch. I think we need a new educational field that I like to call sequential decision analytics. Now, this stands on three foundations: optimization, the field of math programming; machine learning, all over the place today; simulation. If you're going to do anything with stochastic decisions, you're going to be doing something with simulation. The problem is, if you then want to learn anything about sequential decision problems, in any of those other fields, all of those books teach you roughly the same thing, using roughly the same notation, roughly the same tools. It doesn't matter that much where you got your PhD or master's from. In sequential decisions, this is a complete mess. Not only does everybody learn different languages so they can't talk to each other, they learn different tools. So I now have a new book, came out almost a year ago, Reinforcement Learning and Stochastic Optimization. I use those title names just because those are the most widely used. But if you go to tinyurl.com, RL and SO, there's a complete overview of the book, and you can download a few chapters for free. I also have another book I wrote for an undergraduate class. This uses a teach by example style. This is a publisher where the deal is that we will allow people to download this for free. However, I'm in a 6-month window where they say they've asked me not to download it for free, but starting June 1, it will be available for free. But this is a very skimmable book because you can, other than chapters 1 and 7, every other chapter is just a different example, all written in the exact same style, following my format. So very easy to skim. So I think we're ready to start teaching sequential decision analytics. The neat thing about my Teach by Example style book, the one on the right there, is once you see how I'm doing things, you can quickly say, oh, well, I'm going to use my own problem. I'm going to use my own problem and just follow the style. And I really encourage people to do that, to say, look, sure, go ahead and make up whatever problem that you want and just follow the same style. The main thing is it's a certain way of thinking. And then the other book, it's 1,100 pages, so I call it my big book. That's the book you need if you're going to really write code. So if you really want to sit down and see the details, you need the big book. So here's a few additional references of all the URLs. The very last one, tinyurl.com/SDA links, is a web page of links. So if all you do is remember that last link, tinyurl.com/SDA links, it'll have web pages to videos and books and download. Some of them are just explanatory web pages. I even have a series of the courses that I've taught, grad course, undergrad course. I even have outlined a grad seminar that students can get together and teach to themselves, because you're not going to find a professor teaching this material because the faculty haven't been trained in it. And so I really encourage, and if you're an academic, encourage the students to go to that web page. I outline what material to cover in what order, and they can just do it themselves. I have 2 different schools doing this as we speak. Anyway, I thank you very much. I've had a great time.
Okay, thank you, Dr. Powell, for your wonderful talk. So I think we have a time for the question from audience. Anyone has a question for Dr. Powell? Feel free to unmute yourself and ask questions.
Well, as people are thinking, again, go to the tinyurl.com SDA links and notice that somewhere in there will be something talking about courses. And I really encourage you to go to that. I've also got some other links that are just web pages with nice explanations, like the CFA policy. I also have a pet peeve. I claim that our community, all the community sequential decisions, do not know what a state variable is. And I have a tinyurl.com/on state variables. And if any of you are interested and excited about this field called reinforcement learning, I don't think the RL field knows what reinforcement learning is. So I have my own web page, tinyurl.com, what-is-RL. And I think you'll enjoy that because I'm poking a little bit of fun. I use some of the leaders of the field to talk about how I don't think they know if it's a method or a problem. Okay, looks like we got a question.
Yes. Can you read it?
Yes, I can. So I'm a first-year PhD student. I'd like to work in this area, but I did my undergrad for mechanical engineering. Oh boy, start with the Teach by Example book. And by the way, don't tell anybody I'm giving you this information. I'm putting a link in the chat box. You won't find this on any of my websites. Okay, so that link is a free copy of the companion book. Okay, I can't give out the Wiley book. I don't think that's fair. But this book, like starting June 1, this will be available for free. This is the book that teaches you how to think, and it's the easiest to read. You really have to just read chapter 1. And then if you look at the table of contents, you'll see all the remaining chapters other than chapter 7 are just different examples. And after you read a few of them, you'll realize you get the pattern. Now, chapters 1 through 6, the problems were designed to bring out all 4 classes of policies. And chapter 7 says, okay, I've now covered a bunch of examples. Let's pause for a bit and see. We now have seen examples of different state variables, and we've seen examples of all 4 classes of policies. Can't.
Dr. Powell, you know what? Because I think we have to share the link. Let me share the link with the.
I don't have a box in the Q&A where I can enter.
Let me share the link. Okay, I think now everyone can see it.
Oh, wait a minute. Here we go. Oh, I'm sorry.
Is that the right link you want to share?
So I just put it in the answer.
Okay.
Does everybody see it now? It's tinyurl.com, Powell SDAM book, one word, Powell SDAM book. And it's very easy to flip through. In fact, the chapters themselves, even if you go to read it, it starts off with a narrative. Then it has the 5 elements, which are very easy to skim. You don't need to read every little element, but the chapters are all relatively short. And it's just trying to get you to think in the right style. When you come from mechanical engineering, by the way, you might have learned optimal control. So from the mechanical and electrical engineers all learn control. Control is usually taught deterministically, which is really unfortunate. And they, like the Bellman people, they have a heavy emphasis on what they call Hamilton-Jacobi equations. In OR, we call them Bellman equations. And I'm here to tell you, whether you call it Bellman or Hamilton-Jacobi, it is the least useful of the 4 classes of policies. And I will tell you, if you're an optimal control person, my 4 classes of policies can be found all through the optimal control literature. I'm not the first to have discovered these. I'm pulling things from the field. All I do is, like, if you open like one of Frank Lewis's wonderful optimal control books, he'll present the model with Bellman's Hamilton-Jacobi equations all at the same time, as if Hamilton-Jacobi and the model are inseparable. It's completely wrong, even in the field called optimal control. They have something called model predicted control. They have something called linear decision rules. They've already discovered most of the policies that I have. It's not that I've invented these, I'm just sweeping them up. And the one thing that I'm doing is saying model first, then solve. And that's what's not being done. That is the big point of departure. Model first. Now, I have a heavy emphasis on problems that involve uncertainty. Not all problems involve uncertainty. I think most do. And one of the problems with uncertainty is that it's subtle, it's trickier. I really do encourage that people go to the RL and SO website. Go to chapter 9, which you can download for free. It's my modeling chapter. And while you're at it, download chapter 11, which is a very detailed summary of all 4 classes of policies. This is from my big book. By the way, I taught the small book at Princeton at the undergraduate level. And at the graduate level, I had students from 8 different graduate departments, so not just the more mathematical departments. So I'm very much somebody who loves to model the real problem, do practical solutions, and then you can guys go split. Some of you may want to do something more theoretical, and that's fine. I've got a lot of theory that my students like to do. That's Princeton. But I really like the computational side. And I will tell you, the PFAs and CFAs sound simple. Something that I repeat multiple times is the price of simplicity is tunable parameters. So anybody who says, oh, no, that's too complicated, I want to do something simple, I can almost guarantee you, hidden in that simple method is tunable parameters. And tuning is hard. Tuning's harder than people think it is. There's a no free lunch theorem in here somewhere.
Okay, any other questions from audience? I actually have one question for you. So Dr. Powell, you actually show the slides talking about the bridge between machine learning and sequential decision problem. And if you look at the model for the sequential decision problem, the models, we have a time component in there. But in the machine learning, there's no time component in there. So can you talk about the connection between of this?
First of all, in that simple illustration, I am illustrating static batch machine learning as opposed to online learning. There is a category called online learning. Right. However, there's a huge category called active learning where not only is online learning, but I get to choose what I observe. Well, for me, that's a sequential decision problem.
Mhm.
Okay, so if you have just a pure learning problem, but you get to choose and what you choose affects or influences what you observe, that falls in the sequential decision class.
Mhm.
Okay, so chapter 7 of my big book is really emphasizes that. Now, sequential decision problems are inherently sequential. By default, I use time t. There's a lot of problems where I use iteration n.
Mhm.
And I switch back and forth between the two because some problems it just makes more sense to talk about iteration n, and I use that in the superscript. And then there's other problems where there's a natural time component, and which place I do t. So I use t as my default. But like if you go to chapter 7, it's all about sequential decision problems. It's all about active learning problems. I don't know how many people in the audience have heard of multi-arm bandit problems.
Yeah.
Something that you'll see in chapter 7. Chapter 7 has the title, derivative-free stochastic optimization. I came to the realization that every derivative-free stochastic optimization is a multi-arm bandit problem and vice versa. They are just two names for the same thing. So I chose to title the chapter derivative-free stochastic optimization, but if you go into the chapter, you will see a whole section on multi-arm bandit problems. And it illustrates all 4 classes of policies. And that's just pure learning. So you've got the pure learning problems and the physical resource allocation problems and the combined problems.
Mhm. Okay. All right. Thank you so much.
Okay, so the last question, can you explain why we search over functions in sequential decisions? We search over functions because we want to find the best method for making decisions. And the reason why we need the best method at time t is I don't know what the state will be. I don't know what I will know at time t. So I have to have a function that works for any state variable. Okay, in a deterministic problem, I know what I will know at time t. Okay, that's known, so I just pick an x. But in a sequential stochastic problem, I don't know what I'm going to know at time t, so I put it in my state variable. Now I have to have a function that works on any state variable. Do we have a closed form function in the end? Those are called PFAs. And the answer is, if you have a PFA, it's a closed form function. You generally won't have PFAs, but like an order up to policy is a closed form function, but a look ahead policy is not. I mean, anything involving ADP or any type of a look ahead is not closed form. In fact, I would say only the PFAs will be closed form and the other 3 are not, because they are all have embedded optimization problems buried in the policy. So of the 4 classes of functions, 3 of them have an optimization problem inside the policy. I hope that helps.
So I think we kind of run over time, but if anyone has any more questions.
By the way, if you wish, follow me on LinkedIn. I post a steady stream on LinkedIn in the broad domain of sequential decisions, sometimes on supply chain problems. I'm retired from Princeton. It's one of the things that I do is I sit down here in Florida and post on LinkedIn.
Yeah, I think most of the people actually follow you on LinkedIn already, including me. Yeah, thank you so much. I think this is our first Data Mining Society webinar. Thank you very much again, Dr. Powell, for giving this talk. So we will follow up with you if we have any question.
Great. Thank you very much for the invitation.
Okay, thank you so much. Have a great day.